A central processing unit is the hardware within a computer that carries out the instructions of a computer program by performing the basic arithmetical, logical, and input-output operations of the system. The term has been in use in the computer industry at least since the early 1960s. The form, design, and implementation of CPUs have changed over the course of their history, but their fundamental operation remains much the same. A computer can have more than one CPU. This is called multiprocessing. All modern CPUs are microprocessors, meaning contained on a single chip. Some integrated circuits can contain multiple CPUs on a single chip. Those ICs are called multi-core processors. An IC containing a CPU can also contain peripheral devices, and other components of a computer system. This is called a system on a chip. Two typical components of a CPU are the arithmetic logic unit, which performs arithmetic and logical operations, and the control unit, which extracts instructions from memory and decodes and executes them, calling on the ALE when necessary. Not all computational systems rely on a central processing unit. An array processor or vector processor has multiple parallel computing elements, with no one unit considered the center. In the distributed computing model, problems are solved by a distributed interconnected set of processors. History. Computers such as the ENIAC had to be physically rewired to perform different tasks, which caused these machines to be called fixed-program computers. Since the term CPU is generally defined as a device for software execution, the earliest devices that could rightly be called CPUs came with the advent of the stored program computer. The idea of a stored program computer was already present in the design of J. Presper Eckert and John William Mauchly's ENIAC, but was initially omitted so that it could be finished sooner. On June 30, 1945, before ENIAC was made, mathematician John von Neumann distributed the paper entitled First Draft of a Report on the EDVAC. It was the outline of a stored program computer that would eventually be completed in August 1949. EDVAC was designed to perform a certain number of instructions of various types. Significantly, the programs written for EDVAC were to be stored in high-speed computer memory rather than specified by the physical wiring of the computer. This overcame a severe limitation of ENIAC, which was the considerable time and effort required to reconfigure the computer to perform a new task. With von Neumann's design, the program, or software, that EDVAC ran could be changed simply by changing the contents of the memory. EDVAC, however, was not the first stored program computer. The Manchester Small-Scale Experimental Machine, a small prototype stored program computer, ran its first program on June 21, 1948, and the Manchester Mark I ran its first program during the night of June 17, 1949. Early CPUs were custom designed as a part of a larger, sometimes one-of-a-kind, computer. However, this method of designing custom CPUs for a particular application has largely given way to the development of mass-produced processors that are made for many purposes. This standardization began in the era of discrete transistor mainframes and mini-computers and has rapidly accelerated with the popularization of the integrated circuiter, IC. The IC has allowed increasingly complex CPUs to be designed and manufactured to tolerances on the order of nanometers. Both the miniaturization and standardization of CPUs have increased the presence of digital devices in modern life far beyond the limited application of dedicated computing machines. Modern microprocessors appear in everything from automobiles to cell phones and children's toys. While von Neumann is most often credited with the design of the stored program computer because of his design of EDVAC, others before him, such as Konrad Zuse, had suggested and implemented similar ideas. The so-called Harvard architecture of the Harvard Mark I, which was completed before EDVAC, also utilized a stored program design using punched paper tape rather than electronic memory. The key difference between the von Neumann and Harvard architectures is that the latter separates the storage and treatment of CPU instructions and data, while the former uses the same memory space for both. Most modern CPUs are primarily von Neumann in design, but CPUs with the Harvard architecture are seen as well, especially in embedded applications. For instance, the Atmel AVR microcontrollers are Harvard architecture processors. Relays and vacuum tubes were commonly used as switching elements. A useful computer requires thousands or tens of thousands of switching devices. The overall speed of a system is dependent on the speed of the switches. Tube computers like EDVAC tended to average 8 hours between failures, whereas relay computers like the Harvard Mark I failed very rarely. In the end, tube-based CPUs became dominant because the significant speed advantages afforded generally outweighed the reliability problems. Most of these early synchronous CPUs ran at low clock rates compared to modern microelectronic designs. Clock signal frequencies ranging from 100 kHz to 4 MHz were very common at this time, limited largely by the speed of the switching devices they were built with. Transistor and integrated circuit CPUs. The design complexity of CPUs increased as various technologies facilitated building smaller and more reliable electronic devices. The first such improvement came with the advent of the transistor. Transistorized CPUs during the 1950s and 1960s no longer had to be built out of bulky, unreliable, and fragile switching elements like vacuum tubes and electrical relays. With this improvement, more complex and reliable CPUs were built onto one or several printed circuit boards containing discrete components. During this period, a method of manufacturing many interconnected transistors in a compact space was developed. The integrated circuit allowed a large number of transistors to be manufactured on a single semiconductor-based die, or chip. At first only very basic non-specialized digital circuits such as NOR gates were miniaturized into ICs. CPUs based upon these building block ICs are generally referred to as small-scale integration devices. SSIICs, such as the ones used in the Apollo guidance computer, usually contained up to a few score transistors. To build an entire CPU out of SSIICs required thousands of individual chips, but still consumed much less space and power than earlier discrete transistor designs. As microelectronic technology advanced, an increasing number of transistors were placed on ICs, thus decreasing the quantity of individual ICs needed for a complete CPU. MSI and LSI ICs increased transistor counts to hundreds, and then thousands. In 1964 IBM introduced its System/360 computer architecture, which was used in a series of computers that could run the same programs with different speed and performance. This was significant at a time when most electronic computers were incompatible with one another, even those made by the same manufacturer. To facilitate this improvement, IBM utilized the concept of a microprogram, which still sees widespread usage in modern CPUs. The System/360 architecture was so popular that it dominated the mainframe computer market for decades and left a legacy that is still continued by similar modern computers like the IBM Z series. In the same year, Digital Equipment Corporation introduced another influential computer aimed at the scientific and research markets, the PDP-8. DEC would later introduce the extremely popular PDP-11 line that originally was built with SSIICs but was eventually implemented with LSI components once these became practical. In stark contrast with its SSI and MSI predecessors, the first LSI implementation of the PDP-11 contained a CPU composed of only 4 LSI integrated circuits. Transistor-based computers had several distinct advantages over their predecessors. Aside from facilitating increased reliability and lower power consumption, transistors also allowed CPUs to operate at much higher speeds because of the short switching time of a transistor in comparison to a tube or relay. Thanks to both the increased reliability as well as the dramatically increased speed of the switching elements, CPU clock rates in the tens of megahertz were obtained during this period. Additionally, while discrete transistor and IC CPUs were in heavy usage, new high-performance designs like SIMD vector processors began to appear. These early experimental designs later gave rise to the era of specialized supercomputers like those made by Cray Incorporated. Microprocessors. In the 1970s, the fundamental inventions by Federico Faggin changed the design and implementation of CPUs forever. Since the introduction of the first commercially available microprocessor in 1970, and the first widely used microprocessor in 1974, this class of CPUs has almost completely overtaken all other central processing unit implementation methods. Mainframe and mini-computer manufacturers of the time launched proprietary IC development programs to upgrade their older computer architectures, and eventually produced instruction set-compatible microprocessors that were backward compatible with their older hardware and software. Combined with the advent and eventual success of the ubiquitous personal computer, the term CPU is now applied almost exclusively to microprocessors. Several CPUs can be combined in a single processing chip. Previous generations of CPUs were implemented as discrete components and numerous small integrated circuits on one or more circuit boards. Microprocessors, on the other hand, are CPUs manufactured on a very small number of ICs. Usually just one. The overall smaller CPU size as a result of being implemented on a single die means faster switching time because of physical factors like decreased gate parasitic capacitance. This has allowed synchronous microprocessors to have clock rates ranging from tens of megahertz to several gigahertz. Additionally, as the ability to construct exceedingly small transistors on an IC has increased, the complexity and number of transistors in a single CPU has increased many-fold. This widely observed trend is described by Moore's law, which has proven to be a fairly accurate predictor of the growth of CPU complexity. While the complexity, size, construction, and general form of CPUs have changed enormously since 1950, it is notable that the basic design and function has not changed much at all. Almost all common CPUs today can be very accurately described as von Neumann stored program machines. As the aforementioned Moore's law continues to hold true, concerns have arisen about the limits of integrated circuit transistor technology. Extreme miniaturization of electronic gates is causing the effects of phenomena like electromigration and subthreshold leakage to become much more significant. These newer concerns are among the many factors causing researchers to investigate new methods of computing such as the quantum computer, as well as to expand the usage of parallelism and other methods that extend the usefulness of the classical von Neumann model. Operation: the fundamental operation of most CPUs, regardless of the physical form they take, is to execute a sequence of stored instructions called a program. The instructions are kept in some kind of computer memory. There are 4 steps that nearly all CPUs use in their operation: fetch, decode, execute, and write it back. The first step, fetch, involves retrieving an instruction from program memory. Its location in program memory is determined by a program counter, which stores a number that identifies the address of the next instruction to be fetched. After an instruction is fetched, the PC is incremented by the length of the instruction word in terms of memory units. Often, the instruction to be fetched must be retrieved from relatively slow memory, causing the CPU to stall while waiting for the instruction to be returned. This issue is largely addressed in modern processors by caches and pipeline architectures. The instruction that the CPU fetches from memory is used to determine what the CPU is to do. In the decode step, the instruction is broken up into parts that have significance to other portions of the CPU. The way in which the numerical instruction value is interpreted is defined by the CPU's instruction set architecture. Often, one group of numbers in the instruction, called the opcode, indicates which operation to perform. The remaining parts of the number usually provide information required for that instruction, such as operands for an addition operation. Such operands may be given as a constant value, or as a place to locate a value, a register or a memory address, as determined by some addressing mode. In older designs, the portions of the CPU responsible for instruction decoding were unchangeable hardware devices. However, in more abstract and complicated CPUs and ISAs, a microprogram is often used to assist in translating instructions into various configuration signals for the CPU. This microprogram is sometimes rewritable so that it can be modified to change the way the CPU decodes instructions even after it has been manufactured. After the fetch and decode steps, the execute step is performed. During this step, various portions of the CPU are connected so they can perform the desired operation. If, for instance, an addition operation was requested, the arithmetic logic unit will be connected to a set of inputs and a set of outputs. The inputs provide the numbers to be added, and the outputs will contain the final sum. The ALU contains the circuitry to perform simple arithmetic and logical operations on the inputs. If the addition operation produces a result too large for the CPU to handle, an arithmetic overflow flag in a flags register may also be set. The final step, write-back, simply writes back the results of the execute step to some form of memory. Very often the results are written to some internal CPU register for quick access by subsequent instructions. In other cases results may be written to slower, but cheaper and larger, main memory. Some types of instructions manipulate the program counter rather than directly produce result data. These are generally called jumps, and facilitate behavior like loops, conditional program execution, and functions in programs. Many instructions will also change the state of digits in a flags register. These flags can be used to influence how a program behaves, since they often indicate the outcome of various operations. For example, one type of compare instruction considers two values and sets a number in the flags register according to which one is greater. This flag could then be used by a later jump instruction to determine program flow. After the execution of the instruction and write-back of the resulting data, the entire process repeats, with the next instruction cycle normally fetching the next in sequence instruction because of the incremented value in the program counter. If the completed instruction was a jump, the program counter will be modified to contain the address of the instruction that was jumped to, and program execution continues normally. In more complex CPUs than the one described here, multiple instructions can be fetched, decoded, and executed simultaneously. This section describes what is generally referred to as the classic RISC pipeline, which in fact is quite common among the simple CPUs used in many electronic devices. It largely ignores the important role of CPU cache, and therefore the access stage of the pipeline. Design and implementation. The basic concept of a CPU is as follows. Hardwired into a CPU's design is a list of basic operations it can perform, called an instruction set. Such operations may include adding or subtracting two numbers, comparing numbers, or jumping to a different part of a program. Each of these basic operations is represented by a particular sequence of bits. This sequence is called the opcode for that particular operation. Sending a particular opcode to a CPU will cause it to perform the operation represented by that opcode. To execute an instruction in a computer program, the CPU uses the opcode for that instruction as well as its arguments. A computer program is therefore a sequence of instructions, with each instruction including an opcode and that operation's arguments. The actual mathematical operation for each instruction is performed by a subunit of the CPU known as the arithmetic logic unit or ALU. In addition to using its ALU to perform operations, a CPU is also responsible for reading the next instruction from memory, reading data specified in arguments from memory, and writing results to memory. In many CPU designs, an instruction set will clearly differentiate between operations that load data from memory, and those that perform math. In this case the data loaded from memory is stored in registers, and a mathematical operation takes no arguments but simply performs the math on the data in the registers and writes it to a new register, whose value a separate operation may then write to memory. Control unit. The control unit of the CPU contains circuitry that uses electrical signals to direct the entire computer system to carry out stored program instructions. The control unit does not execute program instructions. Rather, it directs other parts of the system to do so. The control unit must communicate with both the arithmetic logic unit and memory. Integer range. The way a CPU represents numbers is a design choice that affects the most basic ways in which the device functions. Some early digital computers used an electrical model of the common decimal numeral system to represent numbers internally. A few other computers have used more exotic numeral systems like ternary. Nearly all modern CPUs represent numbers in binary form, with each digit being represented by some two-valued physical quantity such as a high or low voltage. Related to number representation is the size and precision of numbers that a CPU can represent. In the case of a binary CPU, a bit refers to one significant place in the numbers a CPU deals with. The number of bits a CPU uses to represent numbers is often called word size, bit width, data path width, or integer precision, when dealing with strictly integer numbers. This number differs between architectures, and often within different parts of the very same CPU. For example, an 8-bit CPU deals with a range of numbers that can be represented by 8 binary digits, that is, 28 or 256 discrete numbers. In effect, integer size sets a hardware limit on the range of integers the software run by the CPU can utilize. Integer range can also affect the number of locations in memory the CPU can address. For example, if a binary CPU uses 32 bits to represent a memory address, and each memory address represents 1 octet, the maximum quantity of memory that CPU can address is 232 octets, or 4 GB. This is a very simple view of CPU address space, and many designs use more complex addressing methods like paging to locate more memory than their integer range would allow with a flat address space. Higher levels of integer range require more structures to deal with the additional digits, and therefore more complexity, size, power usage, and general expense. It is not at all uncommon, therefore, to see 4 or 8-bit microcontrollers used in modern applications, even though CPUs with much higher range are available. The simpler microcontrollers are usually cheaper, use less power, and therefore generate less heat, all of which can be major design considerations for electronic devices. However, in higher-end applications, the benefits afforded by the extra range are more significant and often affect design choices. To gain some of the advantages afforded by both lower and higher bit lengths, many CPUs are designed with different bit widths for different portions of the device. For example, the IBM System/370 used a CPU that was primarily 32-bit, but it used 128-bit precision inside its floating point units to facilitate greater accuracy and range in floating point numbers. Many later CPU designs use similar mixed bit width, especially when the processor is meant for general-purpose usage where a reasonable balance of integer and floating point capability is required. Clock rate. The clock rate is the speed at which a microprocessor executes instructions. Every computer contains an internal clock that regulates the rate at which instructions are executed and synchronizes all the various computer components. The faster the clock, the more instructions the CPU can execute per second. Most CPUs, and indeed most sequential logic devices, are synchronous in nature. That is, they are designed with, and operate under, assumptions about a synchronization signal. The signal, known as a clock signal, usually takes the form of a periodic square wave. By calculating the maximum time that electrical signals can move in various branches of a CPU's many circuits, the designers can select an appropriate period for the clock signal. This period must be longer than the amount of time it takes for a signal to move, or propagate, in the worst-case scenario. In setting the clock period to a value well above the worst-case propagation delay, it is possible to design the entire CPU in the way it moves data around the edges of the rising and falling clock signal. This has the advantage of simplifying the CPU significantly, both from a design perspective and a component count perspective. However, it also carries the disadvantage that the entire CPU must wait on its slowest elements, even though some portions of it are much faster. This limitation has largely been compensated for by various methods of increasing CPU parallelism. However, architectural improvements alone do not solve all of the drawbacks of globally synchronous CPUs. For example, a clock signal is subject to the delays of any other electrical signal. Higher clock rates in increasingly complex CPUs make it more difficult to keep the clock signal in phase throughout the entire unit. This has led many modern CPUs to require multiple identical clock signals to be provided to avoid delaying a single signal significantly enough to cause the CPU to malfunction. Another major issue is clock rates increase dramatically as the amount of heat that is dissipated by the CPU. The constantly changing clock causes many components to switch regardless of whether they are being used at that time. In general, a component that is switching uses more energy than an element in a static state. Therefore, as clock rate increases, so does energy consumption, causing the CPU to require more heat dissipation in the form of CPU cooling solutions. One method of dealing with the switching of unneeded components is called clock gating, which involves turning off the clock signal to unneeded components. However, this is often regarded as difficult to implement and therefore does not see common usage outside of very low-power designs. One notable late CPU design that uses extensive clock gating to reduce the power requirements of the video game console is that of the IBM PowerPC-based XBOX 360. Another method of addressing some of the problems with a global clock signal is the removal of the clock signal altogether. While removing the global clock signal makes the design process considerably more complex in many ways, asynchronous designs carry marked advantages in power consumption and heat dissipation in comparison with similar synchronous designs. While somewhat uncommon, entire asynchronous CPUs have been built without utilizing a global clock signal. Two notable examples of this are the ARM-compliant Amulet and the MIPS 3000 compatible mini-MIPS. Rather than totally removing the clock signal, some CPU designs allow certain portions of the device to be asynchronous, such as using asynchronous AL using conjunction with superscalar pipelining to achieve some arithmetic performance gains. While it is not altogether clear whether totally asynchronous designs can perform at a comparable or better level than their synchronous counterparts, it is evident that they do at least excel in simpler math operations. This, combined with their excellent power consumption and heat dissipation properties, makes them very suitable for embedded computers. Parallelism. The description of the basic operation of a CPU offered in the previous section describes the simplest form that a CPU can take. This type of CPU, usually referred to as subscale, operates on and executes one instruction on one or two pieces of data at a time. This process gives rise to an inherent inefficiency in subscalar CPUs. Since only one instruction is executed at a time, the entire CPU must wait for that instruction to complete before proceeding to the next instruction. As a result, the subscalar CPU gets hung up on instructions which take more than one clock cycle to complete execution. Even adding a second execution unit does not improve performance much. Rather than one pathway being hung up, now two pathways are hung up and the number of unused transistors is increased. This design, wherein the CPU's execution resources can operate on only one instruction at a time, can only possibly reach scalar performance. However, the performance is nearly always subscalar. Attempts to achieve scalar and better performance have resulted in a variety of design methodologies that cause the CPU to behave less linearly and more in parallel. When referring to parallelism in CPUs, two terms are generally used to classify these design techniques. Instruction-level parallelism seeks to increase the rate at which instructions are executed within a CPU, and thread-level parallelism purposes to increase the number of threads that a CPU can execute simultaneously. Each methodology differs both in the ways in which they are implemented, as well as the relative effectiveness they afford in increasing the CPU's performance for an application. Instruction-level parallelism. One of the simplest methods used to accomplish increased parallelism is to begin the first steps of instruction fetching and decoding before the prior instruction finishes executing. This is the simplest form of a technique known as instruction pipelining, and is utilized in almost all modern general-purpose CPUs. Pipelining allows more than one instruction to be executed at any given time by breaking down the execution pathway into discrete stages. This separation can be compared to an assembly line, in which an instruction is made more complete at each stage until it exits the execution pipeline and is retired. Pipelining does, however, introduce the possibility for a situation where the result of the previous operation is needed to complete the next operation. A condition often termed data dependency conflict. To cope with this, additional care must be taken to check for these sorts of conditions and delay a portion of the instruction pipeline if this occurs. Naturally, accomplishing this requires additional circuitry, so pipeline processors are more complex than subscalar ones. A pipeline processor can become very nearly scalar, inhibited only by pipeline stalls. Further improvement upon the idea of instruction pipelining led to the development of a method that decreases the idle time of CPU components even further. Designs that are said to be superscalar include a long instruction pipeline and multiple identical execution units. In a superscalar pipeline, multiple instructions are read and passed to a dispatcher, which decides whether or not the instructions can be executed in parallel. If so, they are dispatched to available execution units, resulting in the ability for several instructions to be executed simultaneously. In general, the more instructions a superscalar CPU is able to dispatch simultaneously to waiting execution units, the more instructions will be completed in a given cycle. Most of the difficulty in the design of a superscalar CPU architecture lies in creating an effective dispatcher. The dispatcher needs to be able to quickly and correctly determine whether instructions can be executed in parallel, as well as dispatch them in such a way as to keep as many execution units busy as possible. This requires that the instruction pipeline is filled as often as possible and gives rise to the need in superscalar architectures for significant amounts of CPU cache. It also makes hazard-avoiding techniques like branch prediction, speculative execution, and out-of-order execution crucial to maintaining high levels of performance. By attempting to predict which branch a conditional instruction will take, the CPU can minimize the number of times that the entire pipeline must wait until a conditional instruction is completed. Speculative execution often provides modest performance increases by executing portions of code that may not be needed after a conditional operation completes. Out-of-order execution somewhat rearranges the order in which instructions are executed to reduce delays due to data dependencies. Also, in case of single instructions, multiple data a case when a lot of data from the same type has to be processed. Modern processors can disable parts of the pipeline so that when a single instruction is executed many times, the CPU skips the fetch and decode phases and thus greatly increases performance on certain occasions, especially in highly monotonous program engines such as video creation software and photo processing. In the case where a portion of the CPU is superscalar and part is not, the part which is not suffers a performance penalty due to scheduling stalls. The Intel P5 Pentium had two superscalar ALUs which could accept one instruction per clock each, but its FPU could not accept one instruction per clock. Thus the P5 was integer superscalar but not floating point superscalar. Intel's successor to the P5 architecture, P6, added superscalar capabilities to its floating point features, and therefore afforded a significant increase in floating point instruction performance. Both simple pipelining and superscalar design increase a CPU's ILP by allowing a single processor to complete execution of instructions at rates surpassing one instruction per cycle. Most modern CPU designs are at least somewhat superscalar, and nearly all general-purpose CPUs designed in the last decade are superscalar. In later years, some of the emphasis in designing high ILP computers has been moved out of the CPU's hardware and into its software interface, or ISA. The strategy of the very long instruction word causes some ILP to become implied directly by the software, reducing the amount of work the CPU must perform to boost ILP and thereby reducing the design's complexity. Thread-level parallelism, another strategy of achieving performance, is to execute multiple programs or threads in parallel. This area of research is known as parallel computing. In Flynn's taxonomy, this strategy is known as multiple instructions multiple data or MIMD. One technology used for this purpose was multiprocessing. The initial flavor of this technology is known as symmetric multiprocessing, where a small number of CPUs share a coherent view of their memory system. In this scheme, each CPU has additional hardware to maintain a constantly up-to-date view of memory. By avoiding stale views of memory, the CPUs can cooperate on the same program and programs can migrate from one CPU to another. To increase the number of cooperating CPUs beyond a handful, schemes such as non-uniform memory access and directory-based coherence protocols were introduced in the 1990s. SMP systems are limited to a small number of CPUs while NUMA systems have been built with thousands of processors. Initially, multiprocessing was built using multiple discrete CPUs and boards to implement the interconnect between the processors. When the processors and their interconnect are all implemented on a single silicon chip, the technology is known as a multi-core processor. It was later recognized that finer-grained parallelism existed with a single program. A single program might have several threads that could be executed separately or in parallel. Some of the earliest examples of this technology implemented input-output processing such as direct memory access as a separate thread from the computation thread. A more general approach to this technology was introduced in the 1970s when systems were designed to run multiple computation threads in parallel. This technology is known as multithreading. This approach is considered more cost-effective than multiprocessing, as only a small number of components within a CPU is replicated to support MT as opposed to the entire CPU in the case of MP. In mount, the execution units and the memory system including the caches are shared among multiple threads. The downside of MT is that the hardware support for multithreading is more visible to software than that of MP and thus supervisor software like operating systems have to undergo larger changes to support mount. One type of MT that was implemented is known as block multithreading, where one thread is executed until it is stalled waiting for data to return from external memory. In this scheme, the CPU would then quickly switch to another thread which is ready to run, the switch often done in one CPU clock cycle, such as the ultra-spark technology. Another type of MT is known as simultaneous multithreading, where instructions of multiple threads are executed in parallel within one CPU clock cycle. For several decades from the 1970s to early 2000s, the focus in designing high-performance general-purpose CPUs was largely on achieving high ILP through technologies such as pipelining, caches, superscalar execution, out-of-order execution, etc. This trend culminated in large, power-hungry CPUs such as the Intel Pentium 4. By the early 2000s, CPU designers were thwarted from achieving higher performance from ILP techniques due to the growing disparity between CPU operating frequencies and main memory operating frequencies as well as escalating CPU power dissipation owing to more esoteric ILP techniques. CPU designers then borrowed ideas from commercial computing markets such as transaction processing, where the aggregate performance of multiple programs, also known as throughput computing, was more important than the performance of a single thread or program. This reversal of emphasis is evidenced by the proliferation of dual and multiple-core CMP designs and notably, Intel's newer designs resembling its less superscalar P6 architecture. Late designs in several processor families exhibit CMP, including the x86-64 Opteron and Athlon 64X2, the SPARC Ultra Spark T1, IBM POWER4 and POWER5, as well as several video game console CPUs like the XBOX360's triple-core PowerPC design, and the PS3's 7-core cell microprocessor. Data parallelism. A less common but increasingly important paradigm of CPUs deals with data parallelism. The processors discussed earlier are all referred to as some type of scalar device. As the name implies, vector processors deal with multiple pieces of data in the context of one instruction. This contrasts with scalar processors, which deal with one piece of data for every instruction. Using Flynn's taxonomy, these two schemes of dealing with data are generally referred to as SIMD and SISD, respectively. The great utility in creating CPUs that deal with vectors of data lies in optimizing tasks that tend to require the same operation to be performed on a large set of data. Some classic examples of these types of tasks are multimedia applications, as well as many types of scientific and engineering tasks. Whereas a scalar CPU must complete the entire process of fetching, decoding, and executing each instruction and value in a set of data, a vector CPU can perform a single operation on a comparatively large set of data with one instruction. Of course, this is only possible when the application tends to require many steps which apply one operation to a large set of data. Most early vector CPUs, such as the Cray-1, were associated almost exclusively with scientific research and cryptography applications. However, as multimedia has largely shifted to digital media, the need for some form of SIMD in general-purpose CPUs has become significant. Shortly after inclusion of floating-point execution units started to become commonplace in general-purpose processors, specifications for and implementations of SIMD execution units also began to appear for general-purpose CPUs. Some of these early SIMD specifications like HP's multimedia acceleration extensions and Intel's MMX were integer only. This proved to be a significant impediment for some software developers, since many of the applications that benefit from SIMD primarily deal with floating-point numbers. Progressively, these early designs were refined and remade into some of the common, modern SIMD specifications, which are usually associated with one ISA. Some notable modern examples are Intel's SSE and the PowerPC-related AlTIVG. Performance. The performance or speed of a processor depends on, among many other factors, the clock rate and the instructions per clock, which together are the factors for the instructions per second that the CPU can perform. Many reported IPS values have represented peak execution rates on artificial instruction sequences with few branches, whereas realistic workloads consist of a mix of instructions and applications, some of which take longer to execute than others. The performance of the memory hierarchy also greatly affects processor performance, an issue barely considered in MIPS calculations. Because of these problems, various standardized tests, often called benchmarks for this purpose such as SPECINT have been developed to attempt to measure the real effective performance in commonly used applications. Processing performance of computers is increased by using multi-core processors, which essentially is plugging two or more individual processors into one integrated circuit. Ideally, a dual-core processor would be nearly twice as powerful as a single-core processor. In practice, however, the performance gain is far less, only about 50%, due to imperfect software algorithms and implementation. Increasing the number of cores in a processor increases the workload that can be handled. This means that the processor can now handle numerous asynchronous events, interrupts, etc., which can take a toll on the CPU when overwhelmed. These cores can be thought of as different floors in a processing plant, with each floor handling a different task. Sometimes, these cores will handle the same tasks as cores adjacent to them if a single core is not enough to handle the information. See also: References and notes. Notes. References. External links. How microprocessors work at How Stuff Works, 25 microchips that shook the world. An article by the Institute of Electrical and Electronics Engineers.